Welcome back to your second lecture of this week. This is Physics 360, week 12, day 2, scheduled for release on April 10th, about the Schrodinger equation, the wave equation, and the steady state temperature in a cylinder. Just a reminder about all of your assignments that you have going on right now. Up here, we have what's due today, which is the daily homework that was assigned this week, Tuesday. Due next week, Tuesday, we have the daily homework that's assigned today, and you can see those problems right here, as well as periodic homework 6, and those problems were listed in a previous lecture. A couple things to not forget. One is that test 3 does open on Friday, April 17th. That's a week from today, and will be due the following Friday. There will be an email to come about what content to expect on that test. Also, don't forget about the next draft of your project and when that's due. So check the syllabus for that date. So first, let's talk about the Schrodinger equation. Which is given by negative h bar squared over 2m times the Laplacian of the wave function psi plus v times psi, where v is the potential in that location, equals I h bar times the partial time derivative of psi. So similar to what we did before, we're going to solve this by assuming a separable solution. And that separable solution will have the form as follows. The full wave function will be capital psi as a function of x, y, z, and time, and we'll separate that into the spatial part and the time part, where the spatial part is lowercase psi as a function of x, y, and z, and the time part will be capital T. We're going to plug this into the Schrodinger equation and then divide by psi times t to obtain the following. All of our partial derivatives have turned into full derivatives. You can't really see that within the Laplacian right here, but they are also full derivatives in there rather than partial derivatives. But we now have the left side of our equation that is just in terms of the spatial variables, and a right side of our equation that is only in terms of time. And as before, the only way for this to be true is if each side of this equation is equal to a constant. And for Schrodinger equation, we are going to call our separation constant E, which will stand for the energy. We can solve the t part of this equation right away. And we obtain that t equals e to the negative I times the energy times time divided by h bar. For the spatial part of the equation, we get the following. Negative h bar squared over 2m times the Laplacian of psi plus v times psi equals the energy times psi. And this is known as the time-independent Schrodinger equation. For the rest of what we're going to do now, let's assume that v equals 0 everywhere and consider only a one-dimensional problem. That is, whatever particle we're talking about here is confined to move only along one axis, the x-axis. Under these conditions, our spatial part of our equation, or the time-independent Schrodinger equation, becomes the following. And this is a differential equation that we know solutions to. The solutions to this are sines and cosines. We will need to have a very specific value of k. And that value of k is the square root of 2me over h bar squared. So now we have the form of our general solution to this equation. We are going to apply this general solution to a specific problem, that is the infinite square well, where v equals 0 in some region along the x-axis, and v is infinity everywhere else. Because v is infinite at x equals 0 and x equals L, that means that our wave function must be 0 at these points. And similar to before, this means we are going to end up discarding our cosine solution, and we will need a k value of n pi over L. But we already knew the value of k. We already knew that the value of k was this square root of 2me over h bar squared. And what this means is we can actually solve for the value of e here. And we get a value of h bar squared over 2m times n squared times pi squared divided by L squared. And we're going to define this as E sub n. These are our energy eigenvalues for a Schrodinger equation problem. So now we have our basis functions, given as sine of n pi x over L times e to the negative I e sub n t over h bar. So we can write our overall wave function, our final answer, as a linear combination of these basis functions. And at this point, we could do the rest of the problem similar to how we've been doing all chapter. All we would need to know is the form of the wave function for all x at time t equals 0, and then we could expand it in a Fourier series. So we can find our values for the coefficient b sub n by using our same Fourier sine series we've been using in the previous sections, with bn defined again as 2 over L times the integral of 0 to L of our wave function at t equals 0 times the usual sine of n pi x over L integrated over x. So this is as far as I'm going to present about the Schrodinger equation, but your homework problem is one that gives you a value of the wave function at t equals 0 and asks you to find the appropriate values of b sub n so that you can expand your wave function in a Fourier sine series as we have before. The next partial differential equation I want to discuss is the wave equation, which is given by the following differential equation. The double partial derivative of our displacement from equilibrium y in terms of x equals 1 over v squared times the double partial derivative of y in terms of t. And this is for a one-dimensional string stretched along the x-axis, where y is our displacement. Since the string is along the x-axis and the displacement's in the y direction, we're going to be basically dealing with a transverse wave here. One important assumption we're making that you should be aware of is that we're assuming that the length of the string is equal to the distance between the supports. And the length of the string and the distance between the supports will be effectively equal when the displacements are small. So we're not dealing with large displacements from equilibrium here, and this will make our life a little bit easier later. So we're going to start this problem the same way we have for all of these problems so far. We are going to assume a separable solution. So our displacement y as a function of position and time will be given as a function capital X just in terms of x and a function capital T just in terms of t. We're going to plug this into the wave equation and divide by xt to get the following. And since we have a left-hand side only in terms of x, right here, and a right-hand side only in terms of t, right here, we know each of the sides of the equation here must be equal to some constant. And that constant here, well, we could give it a positive k squared or a negative k squared, but we're going to want sines and cosines here, at least for the t part of our equation, because we assume this wave, the displacement, will oscillate back and forth between positive and negative. It would not make a lot of sense to pluck a guitar string and have the amplitude of that string exponentially increase. So we are going to want sines and cosines here. which means we are going to need a negative separation constant. Both of these equations are pretty straightforward to solve, so we obtain the following forms for capital X and capital T. So x, as usual, is our cosine of kx and our sine of kx, and t here is given by something similar, but instead of a kx on the inside of the sine and cosine, we have k times v times t. And to make our lives easier, we're just going to define kv, which is the wave number times the velocity, as the angular frequency omega. So now we beat it with our boundary functions until we get something more usable. So let's block this part off here and start working on our boundary functions. We know that the displacement has to be 0 at x equals 0 and x equals L. This is because we're dealing with a string like on a guitar, and that string is pinned in place at the ends, so you can't have any displacement there. This means, again, we're going to discard our cosine solutions and use k equals n pi over L. Which means our general form of our solution will be the following, where we still only have our sine solution for the x part, but we have both cosine and sine available to us for the y part. And in order for us to proceed any further, we're going to need to know something about the initial conditions of the string. And there are really two different ways we can give information about the initial state of this string. One of them is we might know the shape of the string at t equals 0. Say the string is pulled back and released right at t equals 0. So maybe we pull the string up by its center, a distance of h, which needs to be small compared to the length of the string, and release it from there. This is figure 4.1 in your book. So, a couple of things we know based on releasing the string from this shape at t equals 0. So one thing we know, the string is released from rest. So at t equals 0, the derivative of y with respect to time has to be equal to 0. And this has to be true for the entire string, for every value of x. Just a brief note real quick, don't confuse the dy dt here with the speed of propagation of the string itself. This is not the same thing as v. V is the speed at which a wave pulse propagates along the string in the x direction, and dy dt is the speed of any given point on that string as it oscillates up and down. So based on this boundary condition, we know that we can discard the sign of n pi vt over L solution, because this will not give us a 0 derivative at time t equals 0. So now we have our basis function. Our basis function is the sine of the x term and the cosine of the y term. And our overall solution will again be a linear combination of these solutions. So now comes the time where we do our Fourier sine series based on our initial conditions here. Using our y0 function from above, we can say that at t equals 0, y should equal y0, which is equal to the following series. The sum from n equals 1 to infinity of bn times sine of n pi x over L, and the cosine term is equal to 1, so it just disappears. And then we would expand y0 in a Fourier sine series, as we've done before. This is actually one of your daily homework problems for today, is to actually do this expansion and show, in part, that we get the following overall solution for our specific y naught that we looked at. Coefficient of 8h over pi squared out front, and then inside the brackets, our first term corresponds to n equals 1, with sine of pi x over L and cosine of pi vt over L. Our next term corresponds to n equals 3, with a coefficient of negative 1/9, and a sine of 3 pi x over L and a cosine of 3 pi vt over L. But, as it turns out, this is only one of two ways we can specify the initial condition of the string. The other way we could specify the initial conditions of the string is to have the string all be at equilibrium at t equals 0 and apply an impulse to the string. So rather than pulling the string back and releasing it from some initial displacement, the string is at equilibrium, and maybe we're going to whack it right at t equals 0 and see how it responds. So basically what we have here is that del y del t will be given as a function of x at t equals 0. So let's give this del y del x at t equals 0 a name, and let's just call this v of x, the initial velocity function. So this time, we need y to be equal to 0 for all points x along the string at t equals 0. So this means we are going to this time discard the cosine solutions of the time component. So we then have our basis functions, given this time as the sine of n pi x over L, that part's the same, and this time we have the sine of n pi vt over L. So our overall solutions are then a linear combination of this. So in order to match the initial conditions we've been given, that initial velocity function, we're going to have to take the derivative of this y function with respect to time, a partial derivative. And with that, we obtain the following. So when we take the time derivative first, we get this n pi v over L term from our chain rule. And then when we plug in t equals 0, our sine of something t term becomes a cosine of something t term, and the cosine of 0 is 1, so our equation just becomes exactly what you see here. So now hopefully you see why I did not use a lowercase b before for my coefficient, because it turns out that everything out here is going to be my b sub n, my coefficient for my Fourier sine series. So writing this in a different form, this will be the sum from n equals 1 to infinity of little b sub n times sine of n pi x over L, and this is going to be equal to our initial velocity function. Here, b sub n is defined as big B sub n times n pi v over L. So then we would expand our initial velocity function in a Fourier sine series to get our coefficients b n, little b sub n, and then use the relationship between the two that is given right here in order to find the values of big B sub n so we can construct our entire series. The only other thing I want to mention about the wave equation problems is what these individual values of n represent here. So if you pick just a single basis function with a given value of n, you are getting the normal modes of this string. So that's all that I plan to talk about the wave function. Now on to probably the most difficult thing we'll do today, which is the steady state temperature in a cylinder. Perhaps not surprisingly, these problems get more complicated when you let them be two-dimensional or three-dimensional rather than just one-dimensional. So in order to solve this problem, let's think of some initial conditions for our cylinder. Let's let this cylinder have a radius of A, with one end on the xy plane held at 100 degrees, and all of the walls held at 0 degrees. So we're also going to hold the end at infinity at 0 degrees, so this is a semi-infinite cylinder. So it might look something like this if I were to attempt to draw a picture. And we want to find the temperature at any point within this sphere once it's reached a steady state. So if we want a steady state temperature, that means we're going to need to use Laplace's equation. Because we're dealing with a cylinder here, it makes sense to use cylindrical coordinates. So I'm going to write down Laplace's equation in cylindrical coordinates, which is given as the Laplacian of u equals 1 over r times del by del r of quantity r times del u del r plus 1 over r squared del squared of u by del theta squared plus del squared of u by del z squared all equals 0. And if you've been paying attention, I bet you know what's coming next. And that is, we're going to assume a separable solution. Capital R of r, capital theta of theta, and capital Z of z. I'm going to keep this little serif on my z to let you know when it's a capital Z and when it's a lowercase c. So now we're going to plug this into Laplace's equation and divide by the overall function, r theta z, as we have before. So when we do that, we obtain the following. 1 over big R little r, d by dr of quantity r times d big R, d little r, plus 1 over big theta times 1 over little r squared times the double derivative of big theta with respect to little theta, plus 1 over big Z times the double derivative of big Z with respect to little z equals 0. So the way we break this up is going to be a little different than before. So we're going to look at the first two terms of our equation here and say that these are functions of not z. So we have r's and we have thetas, but there are no z's in these first two terms. And our last term here is going to be a function of only z. So this means that this part here, the part that is in terms of only z, must be equal to some constant that we're going to call kappa, which has solutions that we can find easily enough of exponentials. And we can already discard one of these right away because we need the temperature to go to 0 as z goes to infinity. We will be discarding the e to the positive kz term because it explodes as z goes to infinity. So now we can rewrite what we have with the z term replaced by something else. So this becomes 1 over big R little r times the derivative with respect to r of little r times the derivative of big R with respect to little r plus 1 over theta times little r squared times the double derivative of big theta with respect to little theta. And then this whole last term just becomes kappa squared, and that all equals 0. So the next thing we can do here, because again, we want to break our function into two here, a part that depends on one variable and a part that depends on another variable. And the only problem we have with that right now is here in our theta term, is this r right here. So I'm going to multiply this whole equation by r squared. So in our first term, this takes this r away from the denominator and moves it into the numerator. In our second term, the r squared in the denominator just vanishes, and our last term, rather than just kappa squared, becomes kappa squared r squared. So now we have things separated as we need them to be, because this piece right here is a function of only theta, and the remaining two pieces of our equation here, the first piece and the last piece, are functions of not theta. So that means our part that we had that was just a function of theta will have to be equal to some constant. So I'm going to take this theta part out here and set it equal to a separation constant of negative n squared, which has solutions that are sines and cosines. We don't want exponentials for our theta functions because it should have periodic boundary conditions. Whatever value you get at 0 radians should be equal to the value you get at 2 pi radians, and if you had a positive separation constant, you would get exponentials, and that would not be possible. So instead, with a negative separation constant here, we get theta can either be sine of n theta or cosine of n theta. We don't know too much about n here, except that it must be an integer, because otherwise we would not have periodic boundary conditions. So if n were not an integer, then theta of 0 would not be equal to theta of 2 pi. For our particular problem we're working on, we do not expect any dependence on theta, because our initial conditions, the base temperature of the base of the cylinder, is rotationally symmetric. So we expect our solutions to be rotationally symmetric as well. So we're going to use the cosine of n theta with an n value of not 1, of 0. Let me fix that real quick. And in this case, capital theta just becomes the constant 1. So let's now plug our new information that we've learned back into the main equation we're working on. So rearranging it a little bit and plugging in 1 for our entire theta piece, we get the following. Little r over big R times the derivative with respect to r of little r times d big R d little r minus n squared plus kappa squared r squared, or if we multiply everything here times r, we get little r times derivative with respect to r of the quantity little r times the derivative of big R with respect to little r, plus the quantity kappa squared r squared minus n squared all times the function big R. And this is Bessel's equation. So we need to decide which kinds of Bessel functions to use here. For our problem, r equals 0, the location at the center along the center line of the cylinder, is included in our solution. So we need the Bessel functions that have a finite value at r equals 0. So we cannot use our Bessel functions of the second kind, which means that the function big R as a function of little r has to be equal to a Bessel function of the first kind of the argument kappa times little r. We have one more major boundary condition to consider here, other than the temperature at the base of the cylinder, and that's going to be a process. So the only other boundary condition we have yet to satisfy is that we need our temperature to be 0 along the walls of the cylinder. So U equals 0 when R equals A. So this means that J sub n of kappa A has to be equal to 0. So let's call kappa times A, let's give that a name, K. And let's let these be the zeros of Jn. So this means that we have a more definite answer for our form of big R of little r, which is J sub n of K, little k, R over A. Now we can also plug this value of K back up here into our solution for Z to obtain our general solutions here, our basis functions. Where, just as a note, we have already decided that we are just going to be using the cosine solution with n equals 0. So cosine of n theta with n equals 0 is for our problem specifically, but in any other problem with a different temperature function at the bottom, these would be your general basis functions that you can expand in. So now some complicated math is going to happen, and I am going to need an entire other page for this. So since we're using n equals 0 for our problem, so that we don't get any theta dependence here, which means we are going to be using J naught as our Bessel function. So this means our basis functions are the following, which looks an awful lot like what we had on the previous page without the sine or cosine of n theta, except for this subscript m that I've put on both of my k's right here. And that's because Bessel functions have more than one zero. So here, k sub m refers to the mth zero of J naught. So that means we have our overall solutions for this problem are going to be U is the sum from m equals 1 to infinity of everything we had here with the coefficient c sub m out front. And we need this to evaluate to 100 at every point along the base of the cylinder, meaning everywhere where z equals 0. So writing out what this means in terms of our equation here is that we need u evaluated at c equals 0, which is the sum from m equals 1 to infinity of c sub m times J naught of k sub m times r over a to equal 100 for every point along our base, every point where z equals 0. So effectively what we're about to do here on, again, I'm going to make another brand new slide, is we're expanding the function 100 in a series of Bessel functions rather than a series of sines and cosines as a Fourier series. So this is going to take a little bit of space. So I'm going to clear off some space and talk you through this. This process is also going to use some material we skipped from chapter 12. So this is not a process I would expect you to be able to completely do on your own from scratch, but I will direct you to the appropriate points in the textbook with the equations I'm going to invoke, and you should at least be able to use those equations to follow what I'm about to do. The important part is that everything I'm going to do going forward is in pursuit of finding all of our CM values, the coefficients we need in this series to be able to write our final solution here. So what we need to do, we need to expand 100 in a series of Bessel functions. And this is going to take some time, some identities, some recursion relations, and just some space. So first, let's write off the formula we're working with. The sum from m equals 1 to infinity of C sub m times J naught of K sub m R over A all has to equal 100. And the first thing I'm going to do here is I'm going to multiply both sides of this equation by the following factor. So I'm going to multiply both sides of the equation by r times j naught of k sub mu r over a and integrate from r equals 0 to r equals a. So this mu that I've introduced is just basically the same as m, but we're using a different subscript or a different index to refer to it. Mu refers to the muth 0 of this Bessel function we're working with. So once we do this, we get the following expression. On the left-hand side, we get the integral from 0 to a of this sum from m equals 1 to infinity of c sub m j naught of km times r over a times j naught of k sub mu times r over a dr. Nope, I lost an r in here somewhere. Let me make some room for that. So then there's an r in between here before the second j sub naught function. And the right-hand side of our equation will then become the integral from 0 to a of 100r times j naught of k sub mu times r over a dr. And we're going to deal with the two sides of this equation separately. So all of my work on the left side of the equation is going to be done in blues, purples, and greens. And all of my work on the right side of this equation is going to be done in terms of reds, oranges, and yellows, so we can help keep these straight because there's a lot of stuff that's about to happen. So the first thing we're going to do on the left-hand side of the equation is we're going to evoke equation 19.11 from chapter 12, which is given as follows. The integral from 0 to a of r times j sub p of alpha r over a times j sub p of beta r over a dr equals 0 when alpha is not equal to beta, and equals a squared over 2 times j sub p plus 1 of alpha squared when alpha equals beta. This is effectively a statement of the orthogonality of Bessel functions. So the only terms that survive from our actual boxed equation in green up here above are the terms where mu equals m. It's worth noting that all of our arguments inside of these j's here in equation 19.11, so here and here, they have to be the zeros of the Bessel functions. So alpha r over a is a 0 of j sub p, and beta r over a is also a 0, of j sub p. And that's good because our k sub m r over a and k sub mu r over a are also zeros of these Bessel functions. What this means in terms of our math, in terms of the function we're dealing with, is that only the terms where mu equals m survive. So we can continue to write the left-hand side of our equation here as, I'm going to change all of my mu's into m's here. So first, I've simplified this to just combine my Bessel functions into one, because my Bessel functions were in terms of m, in terms of mu, but only the mu equals m terms survive, so those are identical, and I can just write them as squared. And then, using the results of equation 19.11, we get that this side of the equation equals cm times a squared over 2 times the first Bessel function of just k sub m, no r's and a's anymore, and that Bessel function is squared. So we've now simplified the left-hand side of our equation, and let's go over to the right-hand side of our equation now. For the right-hand side of our equation, we're also going to be using an equation from a section we didn't get to in Chapter 12, and that is equation 15.1 from Chapter 12. And that equation states that the derivative with respect to x of x times j1 of x equals x times j0 of x. This is a recursion relation. So we talked about the recursion relations and orthogonality when we talked about the Legendre polynomials, and these same ideas apply to the Bessel functions as well, even though we didn't have time to talk about them in detail. So if the statement over in equation 19.11 from chapter 12 was about orthogonality, this statement right here is a recursion relation from Bessel functions. So using this equation and plugging in x equals k sub m times r over a, we get the following. A over km times the derivative with respect to r of k sub m r over a times j1 of k sub m r over a equals k sub m r over a times j0 of k sub m r over a. I'm going to put a little line in here just to make it clear which equation is which in the border between them. So, in case you're confused where this first term out here came from, this a over km term, this is from the chain rule. Our original identity has a derivative with respect to x in it. And I know mathematicians will tell me derivatives are not fractions, but they'll often act like fractions when chain rule is concerned. So if we want to find d by dr instead, we would need to multiply d by dr by dx by dr. Or, writing this another way, we can replace the d by dx with d by dr divided by the derivative of r with respect to x. And the derivative, or sorry, that's not right. We can divide this by the derivative of x with respect to r. And the derivative of x with respect to r is k sub m over a, thus the a over k sub m term. So now we're going to do a little bit of math and cancellation here. I am going to cancel out one of these km over a's from each side of our equation. And then I am going to integrate from 0 to a. So we obtain the following equation here. So on the left side, we end up with the same constant a over km out front times what was inside of that derivative before, which is r, times j sub 1 of k sub m r over a, and it will be evaluated from r equals 0 to r equals a. And the right-hand side of this will be equal to just the integral from 0 to a of r times j sub 0 of k sub m r over a. Well, the left-hand side of this equation, well, when we plug in r equals a, we get a squared over km times j sub 1 k sub m r over a, and the term with r equals 0 vanishes. So this is starting to look an awful lot like our original equation that we have up here boxed in red. The only difference is we've changed our m's into mu's, and since that's just an index, we can call our index whatever we want and we don't have multiple indices interfering with each other. And we have this extra factor of 100 right here. So this means that, I wish I'd used a slightly different color for the work I just did in red. So let's just pretend all of this work I did in red here was pink. So that means this term in our equation right here is equal to 100a squared over km times j sub 1 of km. I made a mistake earlier, so I need to back up a little bit. So let me erase what I've just written here so I can fix my mistake, which is in the term I circled in pink. I forgot to plug in r equals a in my Bessel function here. And when I do, the interior of this Bessel function just becomes k sub n. So there we go. Now I'm ready to write down what the equation at the top is equal to, and it will turn out this integral is just equal to 100a squared divided by k sub m times j1 of km. So now we're finally ready to actually solve this. We can put these last two equations together, because this equation here that I am circling in red is equivalent to the original expression that I boxed in red at the top. And this expression here that I'm circling in blue is equivalent to this expression up here that I originally boxed in blue. So from this, we can then solve for our Cm values and get Cm equals 200 over k sub m times j sub 1 of k sub m. There's one very important thing I want to note here, and it's about, this is a Bessel function of k. Well, didn't we say earlier that k was a 0 of the Bessel function? So shouldn't this be 200 over 0? Are we getting infinite values for our coefficients here? And the short answer is no, we are not getting infinite values for our coefficients, because k sub m are the zeros of j naught, not j1. So j sub 1 of km will give you a finite value, a non-zero value that allows you to find your coefficients. And then once you have your coefficients, you can go back to the general form of the solution from a couple slides ago to be able to write out the series solution for everything else, for the entire problem. One thing I at least want to mention is, what if we have a function at the base of our cylinder that's more complicated than just some constant value? We will actually need to do a double series, so a series in terms of r and a series in terms of theta simultaneously in order to make that happen, and I just don't have the time to cover this right now. So since I'm not going to cover it in lecture, I am not expecting you to be able to do that on a test or on homeworks. That was a lot for today, but it's all very interesting, and we're starting to see things come together from various parts of the course. So in addition to Fourier sine series, we've now seen a Bessel function series. We've used recursion relations and the orthogonality of Bessel functions as part of this solution, and we've seen the Bessel functions come out to play in a problem that has cylindrical symmetry, as we expected when we called the Bessel functions the cylinder functions back when we first introduced them. So these are long, involved problems that require a lot of mathematical trickery in order to solve. So the problem we just did is likely far more than I would ever expect from you on a test. I'm more likely to ask you about individual steps of this process, and I'm most concerned about the beginning parts of these problems, where we assume separable solutions and find our separation constants. Those are the most important parts of these problems to me. But that is everything for today. Thank you for watching, and have a good day.